And let's see if we can just annotate it directly on here. Okay, so we have two vector functions. First question is, are they conservative? Of course, what is it that I have to do to determine whether or not a vector field corresponds to a conservative force? Or in general, in just like the mathematical lingo, you just say it's a conservative vector field. So I, of course, need to take the okay, I wrote it, so it's sort of cheating. Got to take the curl. And everything's in Cartesian, so this is kind of nice. So you've got minus 2 cosine z for an x component, x squared for j component, and then minus sine z for a z component. And I'll use my shorthand, which is not just my shorthand for, this is d by dx, d by dy, and d by dz, I hat, j hat, k hat. And then I'm really careful to remember that the j hat component has an overall minus sign, and I compute this. So I get a minus and then another minus that gives me a plus 2 sine z for the j hat component, and then 2x, which of course is not equal to the 0 vector. So this is non-conservative force. And as such, it's got no associated potential function. Okay. So for the second one, same deal. I'm obviously going through these without showing all the work. If you got tripped up on getting this actual answer, make sure that you can go back through it and get it right. Figure out where you screwed up. Sine z is our x component, 2xy, sine z is our y component, and then so in the master class on writing curls, they always tell you to write the vector functions first because they take up the most space in the determinant. And then d by dx, d by dy, d by dz, k hat, j hat, I hat. Okay, and this turns out to be 0. We get a lot of cancellation. So each one of these terms has 2 terms, and if you get the signs correct, then they all cancel. And in fact, this turns out to be 0, 0, and then I'll write the last term just so you see what I'm talking about. So the last term would be 2y sine, sine z minus 2y sine z. So really the second one was a question about like how good are you with your SIGN signs. And so this, because it vanishes, is conservative. Which means that it has an associated potential function and we will need to find it. Okay, so it turns out we don't need any of this to find the potential function. You don't need the results of the curl because we're going to be integrating instead of taking derivatives. So I can clear all that. Okay, so what I have is that there's some scalar function out there. So there exists some scalar function. G of x, y, and z, just to really drive that home, such that the gradient of g equals g. I think I left this a little bit ambiguous in lecture. If this wasn't a mathematical physics class and this was just absolutely have this minus sign there, which has to do with just the verbal definition of we talk about the work that you're doing on the object itself and not the work done by the object. If you left off this minus sign on the quiz, I'm okay with that because in a mathematics class, it's totally reasonable to say the potential function doesn't have this minus sign in the definition. But in physics, because we're taking like the opposite side of Newton's third law and talking about the work or energy put into the object itself, You know, like the gravitational potential tells you how much energy the rocket gains while it's, you know, moving up to space. So that necessitates that minus sign. But if you missed it, don't worry, just realize it's there in most physics classes. Okay, so this is just the gradient, and this corresponds to 1, 2, 3 individual differential equations. So we have this is acting on the scalar function g. That's why I had room to put everything there. Okay, so now I have g of x, g of y, and g of z. Yeah, so that is nice. So I have d by dx of g is equal to the x component, y squared sine z. And that tells me that g itself is equal to the antiderivative of this with respect to x, so xy squared sine z. But then, because I have a partial derivative with respect to x, there could be some arbitrary and unknown function, I'll just call it capital H, of both y and z. And that would have been partial derivative to y. Never would have seen it. And then likewise, I have minus d by dy of little g of is equal to 2xy sine z. And I take the antiderivative of this with respect to y, and I get xy squared minus sine z. And then because a partial derivative with respect to y would have destroyed any unknown function of x and z, I have an unknown function of x and z. Let's call it s, doesn't really matter, x and z. And I think that needs more than a 1 pixel minus sign. Oops. And then, you know, at this point, it probably gets a little boring. I have minus d g dz equals x y squared cosine z. And that tells me antiderivative with respect to z, I get a sine instead of a cosine. But of course, there could be some unknown function, we'll call it capital T, of x and y. So I should put them in that order. X and y. Okay, everybody okay with that so far?
Yeah.
So this is nice in the sense that if you look at all of these pieces, they're exactly the same. So the only thing that my unknown function of y and z, x of z, and x and y simultaneously could possibly be as a constant. So these three collaborate to tell me that scalar function g of x, y, and z is equal to minus xy squared sine z plus, the traditional way of writing it is g naught. And I'll explain why I completely brain farted here, which is like kind of my issue, bad notation, is that typically little g is a vector. So like just in the morning before my brain wakes up, trying to write it as a scalar function is not a good choice. But does this make sense? This is correct. So we take the gradient of a scalar function and we get the individual components, x, y, and z components, which correspond to 1, 2, 3 partial differential equations with not unknown constants, but unknown functions that we can figure out by comparing. Okay, so second problem, you could make more or less work for yourself if you wanted to. We have the flux of a function going through a surface. This turns out to be a cylindrical surface. And let me explain why. So it's bounded by z equals 0. So z equals 0 is this entire plane. and z equals h is the entire plane of z equals h. So those are the easier bits, I think. And then this last condition is x squared plus y squared equals r. So z can be anything, but x squared plus y squared equals r, that's the equation of a circle in the xy plane with radius r. So the circle intersects here, and we end up with a cylinder. So flat top, flat bottom, and then circular sides. So there's the z equals 0 bottom cap, z equals h top cap, and then the label is defined by the surface x squared. So there are two ways of calculating the flux. You could do it directly. You would have 3 different surfaces, and I have a specification in rectangular coordinates, but I probably don't want to use rectangular coordinates because clearly this is a cylinder. Any clever theorem that I could use potentially to make myself have less work to do?
I'm not sure.
So,
Divergence theorem?
yeah, so ultimately so I'll just write the divergence theorem. So Gauss's theorem, or the divergence theorem, turns this into an integral over a volume. So this is the one that says all of the interesting stuff that's happening in the interior of the volume shows up at the surface. And you can compute whichever one is easier. The reason I'm tempted to use this is because this is a scalar, both sides of this equation, obviously. But this is like the hardest way of computing a scalar that I can imagine, because a is a funky function. A is expressed in rectangular coordinates. This is kind of cylindrical. So maybe I can get away with just computing the divergence and take a derivative. Derivatives make things easier. I have no more vector stuff to deal with after the divergence is taken, so maybe the integral itself is easier. So that's my suspicion, turns out to be right. I'll really quickly go through the way of computing the flux directly. It wasn't impossible in like 15 minutes, but you really had to know what you were doing, and I think 2 people did that correctly, which is pretty awesome for a timed exam. So let's compute the divergence of A. And at this point, you guys know how to take the divergence in cylindrical coordinates, but why would you do that? Because Cartesian is easier, and this is already expressed in Cartesian. And I'll just put that alpha out front. X to the 4th y minus 2x cubed y squared z squared. Okay, the d by dx of the first term, we get an alpha out front, of course, is 4x cubed y. Next term, I get minus 2 times 2 is 4. X cubed y. I really like this so far. And then d by dz of the last term is just 2z. Z. Okay, so these actually go away. You know, you don't really have a right to expect this in general. Obviously, this was like crafted for a quiz problem to reward you for realizing the divergence theorem is a thing. And then alpha to z, all of which look pretty similar in sloppy board writing. Okay, this is nice. I have to integrate alpha to z through the entire volume of the cylinder. And what's the nice thing about z in rectangular coordinates versus z in cylindrical polar coordinates? So z is z, we don't have to do anything to it. So I'm going to have a volume integral, so that'll be a triple integral. Our divergence of A is going to be alpha to z, and then we have, so we're going to use cylindrical coordinates because that makes our limits really easy. What's the volume element in cylindrical polar coordinates? You can use R or rho, doesn't matter.
Is it rho squared sine theta?
So the sine, or did you say d psi?
Oh, it's psi.
Rho d psi, rho d rho d psi dz, right? So this is something with units of length, and then the angle is the one that's funky that we have to deal with by multiplying by rho. So that is a little piece of volume in cylindrical coordinates. Now we have to put on the limits. Limits are really straightforward in this specification. So our z, which is at the end, goes from 0 to h. Our phi goes all the way around the circle, so that's 0 to 2 pi. And then our rho goes from 0 to r, right? So this is the spec for a circle with radius r. And then that's not a terrible integral to take. So rho first, let's put the 2 alpha out in front. Z doesn't change with respect to rho, so we get a 1/2 rho squared evaluated at r and 0, so r squared over 2. And then the phi integral, I have nothing that depends on phi, so it's just 0 to 2 pi. That's 2 pi. And then the z integral, I get integral z dz evaluated at h and 0, so that's h squared over 2. And then overall what I should get is alpha pi RH quantity squared. In general, it'd be good to check units on stuff, but the units on this are kind of screwed. So we have powers to the 5th, powers to the 5th, power squared. So I wouldn't think too much about it. I just came up with something that, you know, vanished if you use the divergence theorem. So any questions about that? Okay, I will sketch what you would do if you wanted to compute the flux directly. Totally fine. You would get an answer. You would have to do a bit more work. So we have integral over the surface AD sigma. How many surfaces do I really have to worry about for this closed surface, individual parts of it? So we really have the top of the cylinder, bottom of the cylinder, and I'm going to call this label, like label of a soup can. Okay. This is my suggestion. If you got kind of caught in a morass of converting stuff and it seemed really rough, I would always do this, is the dot product in a lot of cases will save you from doing a lot of needless work. So we've got alpha, all sorts of yucky gunk, right? So this whole thing. But at least for the top and the bottom, tell me something about d sigma. So remember, d sigma is a vector. It points, it has a size, a magnitude, and it has a direction. So for the top and the bottom, can you tell me anything about this that might make our lives easier? Just say, which way does it point? So which way does the little piece of area point at the top or the bottom?
In the z direction?
Yeah, so at the top, absolutely, we have a plus z direction, so that's plus k hat, whatever its area is. And then here, this would be minus k hat down. So d sigma for the top and the bottom is going to look like this, 0, 0, something. So to be honest, we don't have to worry about any of this stuff. And you'll see something magical happened is when we took the divergence theorem, these were the parts that vanished. When we look at the symmetry of the flux integral itself, look, these parts also vanish, just seemingly for a different reason. So kind of neat. So for the top and the bottom, at least, when we take a dot d sigma, what we're left with is just something that looks like this, either top or bottom. It's just z squared thingy, whatever that area is. Well, I can look at this area and I can see that it's, you could call it dx and dy, but probably at this point we're going to want to convert it into cylindrical coordinates. And then this would be the top or the bottom. So the question is, what is d area? Okay, if we wanted to use cylindrical coordinates, what would d area be? So let me look down, top-down view of this. And this is, probably we want to use cylindrical coordinates. This is a little bit of d area. That part is d rho, right? I'm moving a little bit in the radial direction. What's this part?
Rho d phi.
Exactly, rho d phi. So t, b, z squared, rho d phi. And then the limits are, I go all the way around the circle and I go from 0 to h. So writing that out once, so top and bottom, the difference in between the top and the bottom is really just the fact that at the top z is h and at the bottom z is 0. We get 0 to 2 pi and then 0 to r, z squared, rho d phi. And for the top, that's going to be equal to alpha pi h squared r squared. You can work that out. For the bottom, it equals 0 because z is 0. And that turns out to be the answer we got with the divergence theorem. And that took about the same level of effort. So this was the extra part, and this is what the divergence theorem saved you from having to do, is that stupid soup can label. Because the soup can label, we have a piece of the area, or an area differential element that points in the x and the y direction. And so we can't cancel this stuff off just immediately. We actually have to go through how that would work. And I will write how that would actually work. So for the side, what does d sigma look like? Well, if I look from top down, d sigma kind of looks like this. And if I draw y-axis that points like this and an x-axis that points like this, and generically, the question is, well, this is clearly rho hat. The problem is that I have my function itself not specified in terms of rho. So I could either try to express all of A in terms of rho, theta, and phi, or rho, phi, and z, which is one way of doing it. The other way, which is easier, is express rho hat in terms of I hat and j hat. And rho hat is cosine, phi hat, yuck. Cosine phi, I hat plus sine phi, j hat. Okay, now the question is, what's the size of this piece? Well, so the size of this area is, hey, this looks familiar. We have rho d phi, and then it also goes up out of the board, because this is like a top-down view, times dz is the size of d sigma. So d sigma itself is its magnitude, and we know it points in the rho direction. The size is rho d phi dz. The direction is the tougher part, sine phi j hat. And then we dot that with the I hat and the j hat components. So A dot D sigma, we haven't even integrated yet. We've got this gunk, and then we've got this gunk, and we have alpha x to the fourth y times all of this stuff, cosine phi plus minus 2x cubed y squared sine phi rho d phi dz. So last thing to do is we have integrals with respect to cylindrical coordinates. We're going to take limits with respect to cylindrical coordinates. We've got to get rid of these x's and y's. So x is equal to rho cosine theta, and y is equal to rho sine phi. And you dump that in, and you end up with like a whole mess of sines and a mess of cosines. So I'll just kind of skip to the part where, you know, after you wipe the bloody tears from your eyes, you realize that essentially what you have is something that looks like this. So you have cosine to the fifth phi sine to the fifth, and then here you'll have cosine cubed phi sine cubed phi. And you're going to integrate them, but you're going to evaluate them at the endpoints, 0 and 2 pi. Okay, I don't care how many powers you have. If I have some power of cosines and some power of sines, and I subtract their values at 0 and 2 pi, I'm always going to get 0. So this is the part that was a lot of work and ended up giving you 0. Super gross. Because the thing in the integrand is just powers of sines and cosines. You take antiderivatives, but ultimately you evaluate them at 0 and 2 pi. So kind of yucko, to be honest. The divergence theorem did probably save you 10 minutes and a lot of opportunities to make a mistake on that. So any questions about either of those?